This is a video about cancellation. That is, we're going to look and we're going to be in a ring. And let's suppose we have elements A, B, and C such that AB is equal to AC. Now the question is, does this imply that B equals C? Well, if the ring is a field, say we have ring R, if R is a field, remember a field is such that we have multiplicative inverses for everything. Well, if we have multiplicative inverses of everything, we have, start off with this equality. I can multiply on the left by the multiplicative inverse, and I'll get with the unity times B equals unity times C, so I get that B is equal to C. So we get cancellation in the case that R is a field. When else do we get it? Well, let's look at a couple other examples. For one, if we have the integers, if we have AB is equal to AC, in this case we don't have multiplicative inverses. The only units are plus and minus 1. Those are the only things that have multiplicative inverses. If you want a multiplicative inverse for 2, you'd have to use 1/2, but 1/2 is not an integer. Yet, if we have 2 times 3 is equal to 2 times x, we know that we can just cancel these off, and we'll get that x is equal to 3. That's going to be true in the integers from what we know from elementary school and high school. But we don't get inverses, so we need to look and see what is making this happen. Why do we get cancellation? And so this is what we're going to do. We're going to look at integral domains. That's what's driving z being having cancellation, is that z is an integral domain. What does an integral domain mean? An integral domain, let me remind you, is there are no zero divisors. That is, a times b, what does it mean to be a zero divisor? It means a times b equals 0, but a is not equal to 0 and b is not equal to 0. And we know that that's impossible to happen. There are no zero divisors. Whenever you multiply together two integers and you get 0, that means that either a or b had to have been 0. But let me give you an easy example of where this doesn't happen. If you look at z6, 2 times 3 would be 6, except in z6 we get 0. So 2 is the zero divisor and 3 is the zero divisor. And what this says, what this theorem says, is if you have an integral domain and a is not equal to 0, then you get cancellation. And note, of course, if a is equal to 0, well, you're in trouble, because even in the integers, 0 times 1 is equal to 0 times 2, but you can't cancel zeros. You can't cancel zeros to get 1 equals 2. So that's why we require this. So let's look at this. All right. So we're going to suppose that we have equality first. And we're going to subtract. So we're going to get one side equal to 0. Well, we can look, and what this is begging us to do is to use the distributive law. So we're going to factor out the a. And then we get this. Well, what do I have now? Now I have two things multiplied together to give me 0. And I know that I don't have zero divisors because I'm in an integral domain. And I know that a is not equal to 0. Well, the only option left is that b minus c has to be 0. Because if b minus c is not equal to 0, that means that a is a zero divisor. But there are no zero divisors in integral domains. So we conclude that b minus c equals 0, and then finally, we get that b equals c. And that is the cancellation we need, and therefore we are done with this proof. So we don't need multiplicative inverses to get cancellation. An integral domain, no zero divisors, is sufficient. But we do need integral domain. And let's explore this. If d is equal to z6, remember z6 has zero divisors. It's not an integral domain since 2 times 3 equals 0. Then 2 times 3 equals 2 times 0. But I can't just cancel off the 2's and get that 3 is equal to 0, because that is false. So 3 is not equal to 0, so we don't get cancellation in this non-integral domain. All right, thank you. We're done.